All right, thanks for coming. Let's go ahead and get started. Hopefully this will not take too long. I don't think it's going to take the length of a full regular class. We don't have quizzes, for instance, and I'm not going to be able to answer questions. If you do have questions about this sometime over the weekend, feel free to email me. We could set up a virtual meeting to discuss if that's necessary. But here's how we're going to start. Say we have z as a function of x and y, but x and y are really both functions of t. So in reality, what's happening here is z is a function of t, with x and y are intermediate variables. That is the vocabulary term there, the intermediate variables. So in reality, if you could cut these out, you could have a function, one variable, t, directly to z, skip the steps in between, and that would be a calculus 1 problem. So we want to say then, if that is the case, what is dz over dt? T is really the thing that's driving z. Maybe it's time. And so there are two different paths that it takes to get to z. So essentially what we do is we treat each of the paths as a single variable case and add them together. So we do this first path. It would give me, let's be very careful there. Now z is a function of both f of x and y, so we will say del z over del x. X is a function of t alone, so instead of the partial, we just do a regular derivative, dx over dt. I'm not too strict if you mix up these del's and d's, but other people, including the textbook, are very strict about it. So basically use a regular d if there's only one variable, only one input to whatever's in the numerator. We use these curly partial symbols if there's more than one input. Z has more than one input, so we use a partial. Then we say, okay, let's look at the other path down here. Well, that, again, using the basic chain rule from calculus 1, we'd have del z del y. Using the partial for y means we can ignore the x at this step, times dy over dt. That's really all there is to it, is to say we've got these inputs, these different steps before you get to the output. Sometimes there might be more inputs, sometimes there might be more outputs, but basically is we just want to look at all the paths that travel from this input here to this output here, figure out all those paths using the standard one variable chain rule, and then just add them all together. And this can be generalized in the natural way, which is to say if we have z is a function of x1, x2, all the way out to some xn, then we can say dz over dt, assuming all these x's are functions of t, would be del z del x1 dx1 dxt plus ... all the in-between ones, del z del xn dxn over dt. And usually in this class we won't go past having three different variables, three different inputs, but you could extend it out as far as you want and just, again, go through every possible path. So let's see an example of what we're talking about. And I won't take as much time to leave these things on the board because you can always just pause if you need more time to look at it and copy it down. So example, let's say on a circle of radius 2 will have a height, as in the third dimension, z equals x squared minus 3y squared plus 20. So we have a circle going around this way. What we can do, let's parameterize this according to some t, which would represent the angle. We'll use the standard parameterization, which is to say x is 2 cosine of t, and y is 2 sine of t. So that's nothing new. So then we want to say, what is dz over dt? Essentially saying, if you were on this circle, walking along it, you might not even see the curvature, you might just see the up and down. And so it's basically saying, how fast are you going up and down, regardless of all the curvature in the circle? So dz over dt, we will want to do del x, no, sorry, scratch that, del z over del x dx dt plus del z over del y dy dt. Well, that's pretty straightforward, I hope. Oh, went off the screen there. Let me pull this back. There we go. There. So del z del x, when we look at the z function here and take the x derivative, that's going to be 2x. And then dx dt, so we look at x is 2 cosine t, it'll give us negative 2 sine of t. Del z del y would be negative 6y, and del y del t will be 2 cosine of t. Now, we were asked dz dt, so it's not really good to have all these x's and y's in there if we can write them in terms of t, which we can. So we're going to go ahead and substitute, so we'll have only t in our answer. So we'll have 2 cosine of t. No, wait, hold on. Let's check that again. X is 2 cosine. So this should actually be 4 cosine of t. Because 2 times 2. Negative 2 sine t. Minus 6 times 2 sine t, so that's 12 sine of t. 2 cosine of t. So together, this ends up as negative 8, negative 24, so negative 32 sine of t cosine of t. Or if you prefer, there's the trig identity, which would be negative 16 sine of 2t. I would be fine with you leaving it in this form. And then it says evaluate this at t equals pi over 4. So if we plug in pi over 4 to this, we would get negative 16 2 times pi over 4. This was a second question. It was like a part B of the question was find what it is at pi over 4. So in case you're wondering where I got that from, I just picked a number to plug in. Sign. There's a sign here. Ugh. I'm getting messy here. Happens sometimes. Negative sine, 16 sine of 2 times pi over 4. It's negative 16 sine of pi halves. Sine of pi halves is 1, so it's negative 16. So what that means in geometric sense is if I were following along here in a counterclockwise direction, when I get to the point where the angle is pi over 4, from my perspective, walking on this track, I will be falling at a rate of negative 16, whatever the units are. I don't know, feet per minute maybe. or whatever t is the parameterization, which again I usually think of as time, but it could be anything that ticks off as you go. It might be arc length for all we know. Well, it could be a lot of things. It's probably some form of time. Just not sure what the units would be. But that's the basic idea then. When we're at that point on the circle, that angle, our rate of change is -16, whatever the units are. Some units of velocity. Okay, so that's the basic example. Let's try a different, slightly bigger one. Case 2, where you have multiple independent variables. So with this time we'll say x is a function of two different variables, s and t, and y is also a function of s and t. And z is still a function of x and y. So now z is ultimately being driven by two different things, both s and t, with x and y as intermediate steps. So this is how I see it. Here's an s and a t, then x, y, z. So s and t are both feeding into y. S and t are also both feeding into x. And then after that, they both go to z. So ultimately, z is a function of s and t with x and y in between. So we should be able to figure out how each of the independent variables, s and t, are driving z. So let's look at del z over del t. Let me switch colors here. I was trying to color code things, but didn't end up working out the way I intended. Oh well. I think we'll make sense of it. Del z over del t is. So we say, what are all the paths between z and t? Well, we could go through y or we could go through x. So that means we get del z over del x over del t. Note in this case, each of these functions has two variable inputs. That's why we're using the partials for both, not the solid d's, not the regular straight line d's. Del z, del y, del t. That's the partial for t. And then del z, del s is del z, del x, del s plus del z, del y over del s. And just like before, if there were 3 variables or 4 variables or whatever, we can just have more and more terms in order to deal with them. So let's do an example. All right. Example. Z equals sine 2x cosine 3y. And let's say that x is s plus t, y equals s minus t. I use a little curly t to try to distinguish from a plus sign. And I use z with a little mustache through it to distinguish it from a 2. When I was first doing complex variables, I use z a lot in there, so I got all mixed up because they look the same as 2's. Anyway, let's go through this. Del z, del x. So what is the partial here with respect to x? It is 2 cosine 2x cosine 3y. So cosine 3y is constant with respect to x, so we just do this part. 2 cosine 2x, and then the cosine 3y here. Del z, del y is sine 2x, 3, negative 3 sine 3y. Or negative 3 sine 2x sine 3y. So we need to do all these partials now. I think we can, these shouldn't be too bad though. Del x over del s is 1. Del x over del t is 1. Del y over del s is 1. Del y over del t is negative 1. Those are all my second level partial. I'm not sure if there's a good term for that. All right, so let's work out what the del z over del s is. Well, that'll be del z over del x over del s, plus del z over del y over del s. T is not involved in this one at all because we're not asked for it. We're just trying to get del z, del s for the moment. So let's put the pieces together. Del x, del s is 1, so we'll get 1, 2 cosine 2x cosine of 3y. And then del y, del s is also 1, so plus 1, negative 3 sine 2x sine 3y. Now, we don't want to leave it with x's and y, so we'll replace them with the formula for them. So we get 2 cosine of 2x. Now, x was s plus t. So this is 2s plus 2t. Cosine of y is s minus t, so 3s minus 3t. Minus 3 sine of 2s plus 2t sine of 3s minus 3t. There we go. And that's the answer. Now, I know I said t doesn't factor into it, and it wasn't any of the partials. There were no dt's, yet t is still in the answer. So that happens sometimes. So how fast s is changing does depend on t, even though t wasn't one of the variables we did the derivative of. So it's a little tricky, but this is saying if we knew s and t at any point in their domain, we could plug them into this long formula and know what the overall rate of change is. So with respect to s, I'm saying whatever point it is, if you'll think in terms of the partials again, if you point in the s direction, it's saying how steep it is as you go in that direction, which depends on both s and t in this case. So these can be a lot of work. And again, like I said the other day, there's nothing hard in math. You just have to know how to do a whole bunch of easy things at once. And a lot of what you do in math is take a complicated problem and break it down to smaller pieces that are things you already know. What if we had w is a function of x, y, and z, and x, y, z are each functions of s and t? And that last one, I didn't do the dt, I just did the ds. It will be the same process for everyone. But what this is we got a w here at the top, which goes down to an x, a y, and a z, which goes down to s, t, s, t, s, t. I'm splitting them up. They're just copies here. It's not like it's a different s and t each time. It's just 3 different copies of it. So in this case, if we wanted del w over del t, well, we would say, what are all the paths between w and t? Well, here's one. So del w, del x, del t. Here's one. Del w, del y, del t. And here's one. Del w, del z over del t. And it's a very similar process if you wanted to do for s instead of t. So that's when you have 3 different variables, or really 6 different tracks you could take here. So you just have to combine them in a way that gets you what you want. We could have one that's, let's say, deeper but narrower. This is not a technical term or anything, but imagine this. You got a W, which is based on Z alone, and Z depends on both X and Y. X depends on T, and Y also depends on T. So in this case, ultimately, the connection is from T to W. There are multiple different tracks, but there's really only one input and one output. So we can say a regular derivative, dw dt, one variable, would be, well, let's see what all the paths are. dw dz. There's only one path here, so it's a regular d. Now after z, though, there's 2 paths. So we'll say del z, del x, dx, dt, plus, then the other path, dw dz, del z, del y, dy, dt. And the dw daz can actually be factored out of this. Remember, this is all multiplication. It's not composition or anything, so we can just factor it out. And that would be another way of writing it. Okay, so that's that. So there's a couple more things we want to go through. One of the best uses for this, one of the best things the chain rule is used for, is for doing implicit differentiation. So that is f of x, y equals 0. We've talked about, we have an implicit function defined that way. This determines y as a function of x, at least locally. Something like a circle, maybe technically not a function, but in most places, if you pick a point, you can say, well, in a little neighborhood around it, it's a function, so we can treat it like a function there, and we could work out the derivative there. Maybe that's overly technical. But point is, even though we can't write some nice perfect thing y equals f of x, we're assuming that if you're given an x, you have to find a y to pair with it that makes this thing come out to 0. And we're hoping there's only one y, or at least not too many of them, so that this thing still has a form of give me an x, I'll find you a y to match it. So it's still a function. How do we do this? Well, we can take a derivative of this right here. Let's take the derivative with respect to x. Del x of f of xy will equal del x of 0. Okay, so the right side's obviously 0. I hope that's obvious. 0 never changes. And the left side, well, we'll say it is del f del x times dx dx. Can you do that? Yeah, sure, why not? And del f del y dy over dx. So that's nice and legal. I just used x, one of the intermediate variables, as the base variable, independent variable here. Dx over dx is 1. So move that to our side, we get, instead of del f del x, or just fx equals negative fy dy over dx. So then divide dy over dx equals negative fx over fy. This is worth copying down or memorizing. You know, this would be a really good quiz question. I am going to give a quiz when we come back on Tuesday, so be prepared. I think a question using this formula would be a really easy one to do, easy one to grade. It wouldn't take like 10 minutes like some of these other problems have. So let's see an example of how we would use this. F of xy is sine of xy plus pi y squared minus x equals 0. And note here, this is y is a function of x. Because if I was given an x, I would plug in the number for the x, and then since it's equal 0, I could solve for y. The equal 0 is critical here, because if we didn't have it, we'd have x and y as both being independent variables. But in this case, they're not both independent, because once I'm given one, I can solve for the other one, at least in theory. In practice, I would probably have to make a graph and estimate what the other one would be. But we can find the derivative using the implicit formula. We can say fx is y cosine xy minus 1. And fy is x cosine xy plus 2 pi y. So then I just plug those into the formula. The dy over dx is negative fx, so that's the opposite of what I got there. It would be 1 minus y cosine xy, just multiply by negative 1 and then switch the order, over 2 pi y plus x cosine xy. All right, so that would, again, this would require some 3D graphing if you want to visualize it. But, well, not, well, it would ultimately be a curve of some sort in 2 dimensions. It's just hard to picture what that would look like. I wonder. I'm going to try and graph for a minute. So I don't want to try to stop recording because it'll probably mess up. So if you want to just skip forward a little until you see me start writing or something else pop up. No, I'm not going to do that. I was going to try to go to like Desmos or something and draw a picture, but I'm worried if I do that, I'll mess up the whole recording and I have to start over. So anyway, this has both X and Y in the answer, and that's a shame, but sometimes it happens where you need to know both X and Y to know the rate of change. And again, the simplest example for this is a circle. X squared plus Y squared equals, let's say, 4. That's the example we did earlier with a radius of 2. Then you could rewrite this as f of xy equals x squared plus y squared minus 4 equals 0. Then using the same formula, fx is 2x, fy is 2y, so dy over dx is negative 2x over 2y is negative x over y. And so as long as y is not 0, and y equals 0 would be vertical, because it can't be a function around there, because it fails the vertical line test anywhere close to there. But other than that, if I give you an xy, say root 3 and 1, or negative root 3 and 1, that would be this point here, let's say. That does solve this equation. And if I plug it in, that would mean dy over dx is negative root 3 over 1. So the slope here is negative. Oh, there's a... Wait, what? Oh, there's an extra negative. Sorry, I left out this negative sign. That should be a positive there. So the slope is positive root 3. Which seems reasonable. Maybe I didn't draw it perfectly. I think I should have drawn it further to the left. But that looks about right. And you'll notice I need both the x and the y, because the same x but with a different y gives me a different slope. And so this has some restrictions about it. For instance, you can't plug in y equals 0 because then it would be vertical there. But at any other point, you would say, well, at least around here, it passes the vertical line test, it's a function, and it has a derivative. All right, that digression maybe was a little more advanced than I needed to be. Got caught up in some theory. I want to do one hard problem now. One really long one, and we'll be done, and that is the second derivatives. And that's going to take some work, but we should be able to get there just if we follow all the processes step by step. Z is f of xy equals x over y. And x is s plus t squared. Y is s squared minus t. So I will say, let's find z double s. And I'm not going to do all of them because these take an awfully long time. So I'm just going to work out z double s and hope that's enough for you to get the idea of how this works. All right. So, well, let's do the first partials first. Zx is 1 over y. X is a constant, or no, sorry, x is not, but y is a constant. So take derivative with respect to x, it goes to 1 with 1 over y. Zy is negative x over y squared. That's calculus 1. Pull the x out, 1 over y, or y to the negative 1. Use the power rule to get this. So I'll trust you can work that out on your own. Again, if you have any questions about any of the steps that I skip over, feel free to come talk to me. X sub s is 1. X sub t is 2t. Y sub s is 2s. Y sub t is negative 1. So, we get z double s. We want to really be methodical about this. Z double s is zs s. So let's do this inner one first. We know how to do that. So z sub s would be zx xs plus zy ys. I'm using the shorthand here because if I use the del symbols, this will get really messy. So anyway, zx, so that is, and then there's an extra s out here that we have to deal with later. So we get x, let's see, 1 over y times 1 plus zy is negative x over y squared and then y sub s is 2s. I'm really taking my time here. I suppose you could at this point, if you wanted, just replace the x and y with their s and t expressions and then do it as a one variable problem. But I want to do it this way just because I want to practice with the partials. So let's see. I have here, well, actually, I'm going to back up. Well, we can do this way, but I'm going to show the other way, the way they do it in the book. That was, I want to try to be a little more. That was a mistake on my part. That's all I can say. I meant to do it one way, and I actually did it the other way. Okay, so let's split this s. Zx xs s plus zy ys s. This is a product. These are both products, so we use the product rule. So we get zx s x double s. No, we don't get that. Product rule. Let's think about this very carefully. Derivative of the first times the second. Zx, its derivative, and then not the derivative of the second one. Plus zx x double s. Okay, so we did derivative of the first times the second, and then the first times derivative of the second, where derivative with respect to s each time. I'm doing this in parentheses because this is going to require a chain rule also. Oh boy. All right. This next part is zy s times ys plus zy y double s. Okay. Now I will take a little aside here to say, good news is x double s is 0, so we can strike that part out right here. And y double s is 2, so we're going to replace that with a 2. So this we could clean up a little. We could say 2zy plus zx s xs plus zy s ys. Okay, so we're making some progress here. Now I want to expand out these, figure out what they become. I'm going to leave these in terms of y's and z's and all, and not plug in until the end. So 2zy plus, take the s derivative, so it becomes I feel like I'm leaving something out here. Ah, yes. Okay, trick here. Zx, that is the z with derivative with respect to x. This still has both x's and y's in it. We have seen that even though it's an x derivative, it might have both x and y's. So we need to go through x and y. So what we need is z x y ys plus z x x x s times xs plus z y x x s plus z y y y s y s. Oof. And we have said before that this and this are almost certainly equal to each other, but I'm going to leave them like that for now. All right, so we can now, I think, start plugging in some places. Okay, so 2zy. So if we remember, z was x over y. Maybe you still have it written down in your notes. Zy would be negative x over y squared. So we'll have negative 2x over y squared plus zxy. I'll trust you could work that one out on your own here. It becomes negative 1 over y squared. Just take the x derivative, then the y derivative. That's what you would get. Or the y derivative and the x derivative. It ends up at the same place. Ys is 2s plus z double x is 0. So we don't even need to plug in the xs. And then xs on the outside, though, is 1. So let's see. Yeah. Negative 1 over y squared, 2s, plus 0 times 1, plus, now zyx is negative 1 over y squared. X sub s is 1, plus z double y is 2x over y cubed. Ys is 2s. All times ys, which is also 2s. Maybe we should have simplified this first before we put in the s's. Well, it's a bit of a guessing game to decide how you should simplify or when you should simplify. Well, I guess we had to put the s's in here because you couldn't just have ys. You don't want derivatives in it. All right, so let's see what we have here. So negative 2x over y squared minus 2s over y squared. Distribute this guy. Minus 2s over y squared plus, what would this be? 2x times 2s times another 2s would be 8s squared x over y to the third. Oh, y squared's everywhere. That's good. Yeah, okay. I made a mistake when I was doing this in my notes earlier. I left out a y squared somewhere, and it made it not work out right. All right, so Now, I'm going to try to simplify this before we plug in s's and t's here, because we want it to just be in terms of s and t at the end. But let's try and simplify this before. Let's get a common denominator. So the common denominator would have to be y to the third. We have a y to the third here, and these are y squared, so we can just multiply by y to make them y thirds. So it would be negative 2xy minus 2sy minus 2sy plus 8s squared x all over y third. See, if it's not clear what I did y over y here times y over y here times y over y here to make it be y third on the bottom of all of these. 2xy, 2sy, 2sy, 8s squared x. And now I plug in and I cross my fingers and hope that it matches the answer that's in the book. So let's see, x was s plus t squared. So, or let me combine the like terms here first and maybe take some stuff out. Let's pull out a negative 2 from the top. xy plus 2sy, because there's 4 of them here. When you combine like terms, it'd be negative 4. So pull out negative 2 because it's positive. Minus 4s squared x all over y third. Hope I'm not making any obvious mistakes here. Anyway, with this we get negative 2 s plus t squared. It's x is s plus t squared. S squared minus t plus 2s s squared minus t minus 4s squared s plus t squared all over y to the third, that is s squared minus t to the third power. Do I want to simplify this any? Like I said, I'm doing this one out of the book just because it's such a long problem that I don't want to risk making some mistakes in it. Alright, so we're going to need to expand the numerator. I mean, I shouldn't have factored. Alright, so let's see. Yeah, generally speaking, you want to combine all the like terms and numerator. Denominator is already factored, so if you remember from Calc 1, a lot of times factors will cancel out. That's why you like things in fractions to be factored. But anyway, negative 2, let's see. 4 terms here, so s cubed minus st plus s squared t squared minus t cubed plus 2s cubed minus 2st minus 4s cubed minus 4s squared t squared. I'm feeling better at least because when I tried this earlier I had a 5th power somewhere and I don't know where that came from. So let's see, does anything cancel out from this? Alright, SQ, I don't think anything cancels completely, but there are definitely some terms can be combined. Let's see, negative 2. Alright, s cubed, 3s cubed minus 4s cubed, so negative s cubed. And then negative st minus 2st, so minus 3st. Then s squared t squared minus 4s squared t squared is minus 3s squared t squared minus t to the third. I guess I can take a a negative sign out of these, make those all positive, and this is positive too, over s squared minus t to the third. And that is that right? 2s cubed plus 3st, 3s squared t squared plus... All right, that is correct. Fortunately, I did not make any mistakes this time. Like I said, this is a long process, and it would be easy to make mistakes. I would definitely not give a question this long on a test, but it might be on homework. If you want to practice, this is on page 957 in the textbook, or if you got the ebook, we're in section 15.4. This was example 7, but I only did one of the second derivatives. You could do zst and zts, which hopefully are the same, and you could do z double t. Just practice to see if you can get it to the right place, because it doesn't show all the steps in the algebra. It just gives the answer, and that would be a good way to practice. So, with that said, that covers the chain rule. So, there are obviously more examples I could do, but I'm not going to do that here. I think this is enough to give you the big idea. But like I said, if you would like to meet and ask some questions, just email me. We got this long weekend, but I will be happy to talk to you if that's what you need. All right. Thank you, and I will see you on Tuesday. Bye.